Si tú no...
Yeah, I'll start in a minute. Okay. Share my screen. Okay, you can see my screen, correct?
Yeah.
Yes. Is that the font large enough for you to read? I can make it slightly bigger. Let me make it bigger. Yeah, I want to have today's session interactive, so where you can ask any doubts after describing this, the assignment. I want to open it for discussion, not only on the assignment, but also on all topics related to what you need to use for doing the assignment. Here is the assignment. In the past, I have had the class implement a prototype of a CTL model checker. It's the first time I'm having the class implement, uh, the model checker with a fairly extended scope. Okay, so so you will have the benefit of implementing learning and implementing an extended set of features of the model checker. So it should be fun, I hope. So in this programming assignment, what you will be doing, you will be implementing a simple symbolic model checker, call it CTLMC, to verify properties expressed in CTL. So your CTLMC has to be implemented using the BDD package, and it must support the following features. The set of features that I want you to support mandatorily, and a couple of features that you can do for some advanced marks, advanced points, extra points that I will consider, okay, in the overall in overall grading for the entire thing. So it won't go waste if you try and do that. The extra optional parts of the assignment as well. So the first part is, task one, the problem one. So what your program should read in the following inputs, all assumed to be expressed in kind of essentially lib-compliant fashion. So it has to take in the formulas representing the transition relation and the initial condition formula characterizing the initial set of states for the Kripke model. And an arbitrary CTL formula that can include all CTL operators, all legal CTL operators, EX, AX, EG, EU, AG, AU, ER, and AR, and to any level of nesting of these operators. And of course, at the atomic level, some predicates on the state of the Kripke structure. And outputs, the program should output a yes or no answer indicating whether the input formula holds in the given Kripke model. Additionally, it has to produce a suitable witness to the verification. So that will be, be problem 4 that will be described below. And the third part is, the same verification should be be done, should be able to do under fairness constraints, a given set of fairness constraints. So this feature inputs a finite set of formulas, F, representing the individual fairness conditions from some finite n, and it checks the given CTL formula on only the fair paths defined by F.
Sir, this assignment is to be done in pairs?
No,
Okay.
there will be one other programming assignment, okay? That will be on inductive model checking, okay? That will be using SAT solvers. And that, I think, is a little bit more involved, okay? And that I want having it in pairs here. Right. The counterexample generation consists of generating a suitable witness, that is a path in the Kripke structure as a proof of validation or violation of the input formula. For example, if the formula is of the kind AF of P or some universally quantified CTL operator with a nested formula, then you produce a path for a violation of this. And that should have a path from an initial state for which the negation of that formula, e.g. of not P, holds. If the formula is e.g. of P, then you produce, if the formula itself uses an existential operator, then you produce a path on which P, you produce a witness to the satisfaction of that. Okay? So which means essentially even the, so you need to produce a witness to some existential. So it is reduced, the counterexample generation method is reduced to one of finding the witness to an existentially quantified CTL operator. Then you have just, this task 4 will have to be done without taking into account fairness constraints. Okay? We haven't discussed the technique, the basic technique for counterexample generation, but we will do that, okay? And I will describe it in today's discussion itself. All this thing is the topic of chapter 8, which includes the BDD of the book. It's very detailed. And
so which algorithm we have to use for CTL model checking?
I will get to that. Okay, I will get.
Which book is this? The Edmund Clark one.
Excuse me.
Which book? Which chapter 8
That is
from which book?
whenever I say the book, I mean the
Clark
reference textbook. Okay, Clark,
yeah.
et al. Okay, the book on model checking. So chapter 8 is the topic of chapter 8 is BDDs and implementation of CTL model checking using BDD. So pretty much it is all the algorithm is described there. And we have already seen the algorithm. He doesn't give the code there. You remember that. I will discuss. You've already seen the basic structure of the code using fixed point. Okay, you will be computing fixed points using the iterative method of clean iteration. So that's all you will be implementing. Okay. I will discuss today. So, and if you have, so I'll address some of the basic questions that all of you would have that you need to understand to be able to implement it. I'm sure that as you think about this problem and you read that relevant parts of the chapter, you will have more questions.
Will we be given sample code, or we have to build everything from scratch?
No. So see, the pseudo code is already there. I've already discussed in the at various points in this, and I will summarize it. Okay. So all you have to do is take that code and implement it in the language of your choice. The sample code. So you already have sample pseudo code for what you call, the different parts of the algorithm that you need to use for these things. Okay, and so that you will have to just turn it into a code in a language of your choice. Now, the only part, okay, that where you will need to have is some kind of an interface. You have to eventually use BDDs to manipulate these to construct the formula from the input. You have to construct the BDD, for which maybe we can we can arrange to give you a sample code. Okay, that part, just like for SAT solvers, so we gave some sample codes, that we could do using the interface. You've already been, Zubin already showed you a snippet of how to use maybe more extensive code for how you will use that, what the API is. We can actually do a session, if not today, another more detailed one. Okay? Other than that, what the algorithm that you need is pretty much is in the book, and I have actually covered in the class, which I will summarize again today. Okay, and it should be more clear. So this is the optional part. It's the more advanced part. So where you one part of that is extending the counter example generation with fairness constraints and actually implementing the AX and EX for partition transition relation. Okay, so they are optional. Okay, so that is the overall task. The questions, one of you already asked, what is the algorithm? You said, what is the algorithm I have to use? Okay, by now you should be, you should be clear. You just use the fixed point cleaning iteration algorithm, for which I already showed you a basic structure of the code to iterate it from bottom, or to iterate on a descending chain from top. That is what it will be, and it's only the basic the function that you will be iterating over. The tau function will be different for different operators. Okay, and so I'll be addressing that particular question here, and hopefully that should be clear. And then you could ask further questions. I will be covering the following questions, which all answer at to a different degree. What the question that was posed: what is the code that you'll be using? What is the algorithm that you'll be using? Okay, the sample code part of it, as I said, is already there in the textbook and in the in my lectures slides that I've covered. But we will try to get some sample code for the way that you need to use the BDDs for this purpose. So the main questions are, what is the top level structure of the code for solving problem P1? Okay. Suppose you had something like this. Your input can be something like this, a nested sequence of CTL operators. This is AF of EG of AX. ending with some atomic formula. This is the kind of input that you will be doing. You can assume that this is, yeah, so yes, yes, you have to read in these kinds of things. So in the presence of fairness constraints, how will the basic structure of the code will get changed? That I will also discuss. If you may recall that model checking in the presence of fairness constraints was also expressed as a fixed point computation, as an instance of a fixed point computation problem, okay? Therefore, all of them will use pretty much the same basic algorithm, okay? It is just something at the basic level, the function that gets changed. Now, the technique for generating counterexample is something that will be new that I will discuss, okay? There is some extra piece of code that you will have to add to this during the fixed point computation. Okay. So let me visit some of the, so I'll start with this. So here is the code. This is the code that you'll be using, okay? Pretty much either this one, so because some operators are expressed as computing fixed point of and the least fixed point, okay, starting from false. And all what is what the tau that you use. You have to define, you have to implement the basic the tau. Okay, so in this case, you see, I've also given you the tau. And the first task will be, but yeah, so basically for those operators that have been, for which which are defined as the least fixed point of a particular tau, you'll be using this code, okay? But what you'll have to implement in terms of BDD functions will be this. So tau for each operator, the tau is already defined in the table. We did consider EX, AX, EG, and EF, okay? And for the other ones, AX, etc., they are converted into these using negation, so you could use them, okay, once you construct. So once you have to figure out how to implement this in terms of BDD. Okay. So, for example, this is the code for Okay, for example, tau of z. So forget about the first one, the last bullet. So the tau of z to implement EU is exactly given here. So this is defined as a formula, okay? Now, I already have shown you how to construct EX of F in terms of this. So once you have, and each of these you should implement in terms of BDD operation. So you will take T input once T SS prime, okay? And F as part of the formula. Then you construct this thing using BDD operations, okay? So you will have to build a BDD corresponding to TSS prime. And Zubin already showed you that code, how to build the BDD for an arbitrary formula. So here, once you construct the BDD for TSS prime and FS, FS prime, then you do the apply operation. That's already there in as one of the library functions in BDD. Similarly, existential operation is also there as BDD, as a BDD operation. Okay, so you can actually directly use them, and then that's how you implement tau. Now, in this case, this is the one that you'll have to do. So because this one is expressed in terms of EX, so tau will have to be implemented in terms of EX. So the whole thing will be defined as in terms of BDD composition of BDD operations. And then, so once you construct this function, after that, it is just a iteration of tau. Okay, so tau itself is a BDD constructor. So each time you will be starting with false. Okay, and you take the tau of that, and that you will be using as the input to the next tau, like exactly what is shown here. So this is the code that you will write. It is as simple as that. Okay, all the work gets done in inside the tau operation as BDD. Okay, as manipulating BDDs.
Sir, I actually did not understand how you are using BDD here. BDD only all works for Boolean things, right? Here
Yeah,
the
what is not Boolean here?
S dash is not Boolean, right?
What is not Boolean?
The states
What?
of
No. The states are just variables. Okay. When you say Boolean functions. So what are BDDs? BDDs are representing Boolean functions. TSS prime is a Boolean function. And S and S prime are the variables. And then S and S prime can be a whole bunch of variables, each a bit variable. So you have maybe, yes, those are still Boolean formulas, no? And there is a BDD for a Boolean formula. And existential quantification elimination is an operation on the Boolean formula, which is so on BDD, and the BDD will take that operation will take a BDD. You already saw how you do and ors. We showed that. So that will just produces the BDD, which is the result of applying the AND on those two BDDs. And BDDs are formulas. And the variables there are part of the data structure they're stored in the nodes.
No, sir, I did not understand actually. I mean,
Well, yeah, I mean, okay, so maybe, okay, so what, yeah. So we'll get it. So this, I mean, you have to be, can you be a little bit more specific? What is it that you didn't understand?
the S dash here is a state, right?
Okay,
We are
maybe
not quantifying our Boolean variables.
Yeah. So Zubin, if you're there, can you show your code back? And this is Kapil, right? Who's asking this question?
Yes, sir.
Okay. So maybe he's I think I kind of understand what he's saying. He's still not completely comfortable with when you So when you take two Kapil, I mean, does the rest of the class have a similar doubt here? So you can they be I think I kind of get what Kapil is doing. He's not comfortable yet, completely comfortable with viewing formulas as BDDs, okay? Because they are not, exactly, thing. So does the rest of the class also has a similar doubt?
I have.
Who is this?
Arkadeep.
Who? I didn't get your name. You have to speak up.
Arkadeep. Arkadeep.
Argadi. Okay. So, Zubin, I will make you things. This is very basic. Okay. So let me see. Somebody's doing some chat. Rishikesh P. So this is yeah. So I think we need to before I get into the high level things, we'll have to get the thing clarified. Okay. So what we'll illustrate is okay. So all of you who are having trouble, you understand these as a formula, do you? Do you or don't you? So this is a formula, correct? T appears as a formula. So you understand this equation, that the right side of this Ex of f within square brackets, in some sense denotes the right side formula, in some sense represents or characterizes the set of states. Do you understand that?
Yeah, that much.
Yeah. So what you're doing is this can be constructed as a formula in CNF form or some as you would give it to a SAT. Okay. You could do that. Okay. And every satisfying assignments of that will be a valuation for the variables, assignment to the variables S and S prime. And if S and S prime are vectors in the sense that there are more bits, it'll give you valuation for those things, correct? So, and every valuation will be a satisfying instance of this formula, which will be the state included, which will be a state included in the set of states that satisfies Ex of f. Okay? So, BDD is another representation, just like CNF, BDD is another representation for this formula. And the way it is constructed is, you first construct TSS prime. That itself can be a formula, having lots of connectives. Eventually, eventually it'll end up with variables, correct? And then you will have to construct that. Once you have a BDD for f of s prime and TSS prime, then you do the AND to construct the BDD for that. Okay. And yes, and then you will, existential quantification is, is also an operation. Okay. So which gives you the effect of plugging 0 for one variable, for a particular variable S prime, and then 1 for that, and then taking the OR, and that's exactly what.
I think in this case, a sample code will be more helpful to understand.
Yeah, so that's what I'm trying to see. That part, I just wanted to know that if you understood this particular thing, okay? So as a logical formula, you have no, I am assuming that you understand this one, okay? So now, Zubin, if you could show a code that you showed where it takes two formulas, okay, which you kind of go through a little bit slowly, and then do the AND operation. You start with the AND operation, then you will construct the BDD, display that, which is something that you did last time. Maybe you went, so they missed some of the thing, and then you can actually produce some satisfying instances of that. Okay, can you do that?
Yeah.
Okay.
Right
So
now.
I'm going to make you. So then I hope that'll be clear, guys. Okay. So because you need to, without understanding that, you will not be able to take the next step. Okay. It's good that you asked that question. So let me stop sharing. make so you are a co-host now.
You can see my screen, right?
Yeah.
Okay. So, uh, so the manager is something we have to create for just interfacing with the library.
Make it bigger.
Yeah.
Good.
So we can make new variables using the manager using this ith_var function. So we make variables 0, 1, 2, 3, and we can then use these variables to construct formulas. So an AND formula will take two.
First, I think it was good that you had the formula in logical notation. Please, yeah. So
Yeah.
have the
So
okay.
this is
So
okay. This is out of
yeah,
date
so
now.
Hover, Kapil, and others who asked this question. So this is exactly this piece of code here that Zubin is demonstrating is creating a BDD for this, okay, for that formula.
So this this will create its own BDD. This will create its own BDD, and then we can combine those two with an OR. So that's and this is the BDD that we end up with.
Yeah, but I think you should also, just like in SAT, you can generate the satisfying instances. What is the operation that you do that you would do?
Yeah. So we can.
Yeah, you can show them in the standard BDD because they may not be familiar with the zero arc BDD
Yeah.
notation yet.
So if sorry. Yeah. So now this is the standard notation. This is not the zero arc BDD, but one thing we can do is we can evaluate the BDD. So this is OR of ANDs. Let's call this our BDD equals. So this BDD corresponds to this formula, OR of ANDs. So one thing we can do is we can evaluate it giving certain variables. So we can print out the evaluating this BDD with the valuation 0, 0, 1, 1. So this should give us false, right? No, sorry. This should give us true, yeah. Because if we set V2 and V3 to true, then the entire thing becomes true. If we set one of these to false,
My question was here in that formula S and S dash are states. That's an abstract something, right? It's an abstract quantity, not a Boolean quantity
No,
exactly.
Kapil. For example, the state can have two state variables. Say, okay, it's a two bit state. So V1, V2 can be S, V3, V4 can be S prime. So the T transition relation, which relates S and S prime. Let's suppose your transition system, the state has 2 bits, okay? Which you imagine that it has 2 bits. You constructed transitions with 2 bits. So the variables will be the state variables. So what is represented as denoted as V1, V2 here, read it as S dot V1, S dot V2, okay? And S prime is S dot V, V1 and S dot V2. So you just used a different variable name here. That's all. So what? Okay. So what is abstract about SNS prime? SNS prime, we know that we have all of them. The fact that you're encoding them as Boolean variables, which you've already done using SAT. Here is a different representation than what SAT was using, but the variables are still all Boolean, ranging over a Boolean, and S is ranging over maybe some number of bits, but
But
essentially they
I
are bits, no?
still don't get any idea how to complete this assignment. I'm just not sure how to begin at the first place.
No. First, I'm answering your question. Okay. You asked me your question was how do you do S? Okay. I mean, how do you represent S? What is S? Can you not imagine this TSS prime as, the transition, this formula is a transition relation with S and S
I think
prime?
an example would help,
Example like what?
like a Kripke structure and a step-by-step procedure how to code it up.
Okay. Um, let's see. So maybe that's a good idea. So one of the same things, you could define the mod counter. I know. I mean, even if it takes time, that's okay, Zubin. Define the mod. For the mod 3 counter or something, or you make it even simpler. There was this rotating thing. Now, what would be the simplest thing? So I think he's saying that, to show it in terms of transition.
What would be the input as a Kripke structure here? Means how it will be represented?
I'll answer that by another question. Okay, on your SAT assignment, in your first assignment, how did you represent the Kripke structure?
By a transition relation.
Correct. How was the transition relation represented?
By a formula, I guess.
It's a formula. So what more is being done here? So right in front of you, there is a formula, which is B1 and B2. The only difference is that what is SNS prime was the only thing. So this is also a formula. So there for the SAT, there was this step, okay, whatever was the formula in CNF was directly, that was the formula, okay? So you did construct a formula, right? Before you shipped it off to SAT, didn't you? Yes or no?
Sir, I cannot imagine actually. I think I desperately need an example to work with.
Yeah, no. I'm trying to help you by asking the question. I'm not trying to put you in a spot or anything, but I'm trying to get the thing. So, I'm trying to help you by asking a question related to SAT, so that I can see where you're having a problem. Okay. So the transition relation, it can be a formula representing the transition relation. Do you agree?
Yes.
This formula.
Mm-hmm.
So when you send it to SAT, what do you get?
It will give a satisfying assignment. It will
satisfying assignment,
tell whether it's satisfiable or not.
Correct, which is exactly what is being done here now.
Yeah, exactly. I understood, but given a Kripke structure just as a transition relation, how I can deduce the number of states and stuff?
So the number of states will be the number of inputs of the transition relation, right?
Okay, I need an example for that. I cannot imagine it.
If you have a transition relation that takes 3 inputs, then your state is 3 bits, right?
Yeah, state is 3 bits, but how many states are there? How you can answer?
2 to power 3.
Why do you need to get the number of states? Okay, let's suppose, I think one example involving the computing the set of all successor states. Okay, suppose you do, yeah, maybe we should, even a small assignment, even assigning them so that they can work will be good. So that may be a good idea. So just like you did the SAT example, the fixed point example, how did you do? So you gave T, you did, you know, transition relation twice, correct? There. I mean, in order to get the set of all states that you did thing, I think create this example, Zubin. So you define the transition relation, okay, which all it does is it maybe flips. That's
Yeah,
what.
this is that one.
Okay. So now apply the transition relation twice.
So we can do sorry. So we have a
So you
variable.
need two variables, no?
No, because we can operate on formulas. We can just do the output as a.
No, don't do that, okay? Because you know you want them to do exactly the way that it was done, okay, in SAT,
Okay.
and the way that we have defined Kripke structure, so we don't confuse them further. So do trans AB, and that should be trans AB should be a formula which says B is equal to naught of A, okay? Which, and you create a formula for that.
So
So does the BDD package give you all the satisfying assignments?
yeah, it does.
That's what he's getting to.
Oh, okay,
Over
okay.
here for
Like
the earlier
it
formula.
gives only one satisfying
Yeah,
assignment.
so BDD can give you
Right?
all of them. So
BDD can give you all of them. It's actually
Oh, okay. I'm understanding now. Okay, okay.
so you
no.
get
I don't think. I think please complete the. Where did you switch off? Okay, first
no,
let's
I
go
was
one step at
showing
a
him.
time, Zubin.
Yeah, I
Okay.
was showing him how we got all.
No.
satisfied.
Don't jump. Don't jump. Okay. I mean, just because he answered, I mean, we'll eventually answer that question because he also, I mean, people also asked that how do you do it? Okay. So trans AB is why are you using exclusive OR?
Because there's no equal to.
Okay.
So
There's no equivalent.
yeah, there's no. I don't think I couldn't find it.
Okay. So negation of exclusive OR is fine. Yeah. Okay.
Yeah. No, just
Sir, I think this
exclusive OR,
assignment
right?
without actually counter example is already, I think, hard enough. Don't you think so?
See, you don't take the role of a teacher here, okay, to decide what you
I,
have to do and
I
so on.
just thought it would be much more harder. Means I think doing this itself is going to be very, very hard. So I just
I repeat what I said. You don't take the decision, okay? I mean, I'll take that as a feedback. You know, if does everybody think that way? Maybe I can understand that maybe we should, before you get started on this, it might be a good idea. So that I'll take that as a feedback. And I think people should speak up here. I mean, it's good that Kapil is speaking, but if you just stay quiet, then, you know, we will not get anywhere. So would you think it will be better, you know, in addition to getting some sample code, to maybe getting an assignment where you will do exactly what you did with the SAT formula using BDD, okay? So that as the SAT assignment using BDD, even if it means before, you know, you work on this CTL model checker. Now that part, whether it is, even before you know what is involved, I don't think this proclamation that this is too difficult and that is too easy will be productive, okay? Because that I will decide, okay? So first, so you make, getting some warm-up exercises to get you to the point where you feel comfortable with BDD. That if that can help, I mean that I'm sure will help. That I will arrange. Okay, and so once you get the hang of it, this is not a very difficult exercise. Okay.
Sir, I am actually getting it now.
Yeah.
That how the transition relation works and how the BDD works. I'm getting
Yeah.
it now.
The other people are very quiet. Does that mean that you guys don't have the same doubts as a Kapil? I mean, Kapil at least is brave enough, and then good that he's asking. So, and then you just people just have the same questions, but don't ask. Then what? Why are you? What are you afraid of? You have to speak up. Okay, I'm okay if you unmute your microphones here.
So I have some yet higher level doubts, like as in, so
Yeah, I mean, okay, the higher level doubts regarding the problem itself. Huh?
no, not the problem itself, but like, so okay, so I'm just going to say this basically. Are we going to represent the Z, the predicate itself via BDD, and so the predicate transformer would be a function that takes in a BDD and gives out a different BDD?
Correct.
Right. Okay. That is one thing, and the other thing is when we say that we'll take the transition relation in as an SMT-lib expression. So basically, we'll have to basically work with the Boolean fragment of SMT-lib syntax and parse
No,
that.
yeah, then maybe the SMT lib part. Yeah, I made up
So I
SMT.
think we should give them a parser or something like that, right?
But what would be a good thing? So you could
Yes, sir. A parser would help
yeah,
because
yeah.
But it depends on what language you're implementing it in, right? If everyone's implementing
I
in
think most of people would do it in Python, right? I would means
I was looking. I mean, I'm personally probably going to try in C++ first.
okay.
I guess that part in
or we can just encode it as integers or something.
Yeah, I mean, if we can specify a really simple to parse syntax,
Yeah, we
that would
will
work.
give a syntax that's just integers, like a or something like that, like a sequence of integers or something.
no, but I mean, I thought that SMT lib using prefix notation was the simplest thing. I mean, maybe the parentheses, etc., will put you off, or what?
I mean, you're writing a parser for something like AX or AB, something like that won't be that difficult.
Which is what
if you accept it in this
SMT lib
syntax.
is, huh?
Yeah.
I mean, writing the parser would be fine, but like,
Yeah, but it's
but syntax itself should be like, as in, yeah. So we're going to just go with whatever SMT-lib syntax is, right?
yeah,
That's
and
what
with
I was
special
suggesting.
operators for whatever.
So the only thing is you will have functions or predicate symbols denoting the CTL operators. The rest of it is all logic, okay? And, and then, I mean, the operators of your input formula will be AX, EF, and so on, yeah?
Yeah.
Yeah, so Uh,
Go line by line,
Yeah.
Zubin.
So
okay.
do you have a solution to this assignment ready? Means I just wanted to see it in action.
Which is what Zubin is trying to do.
Okay.
Yeah. So we define a transition relation A and B where we flip the bits every time between. It's basically B equals not A. Then we use three variables, uh, v1, v2, v3, and we define this helper function AND, which is just the AND of two formulas.
But where is the variable corresponding to A and B? That is not.
This is just a transition relation,
Hmm.
but the variables are v1, v2, v3. So
Okay.
in the end, we plug them into here. So we ask for all satisfying instances. That's
No. There is still
But this we say there exists.
What is AB?
So we say v1 relates to v2 via
Okay.
the transition,
Okay. You're
and v2 relates to v3,
okay.
and we're saying there exists some v3 such that this is true. So we're
So
looking
where
for.
is the BDD constructed here? Tell them, where is the BDD constructed? Where is the BDD operations that you are invoking?
So all of this constructs one BDD, this constructs one BDD, this constructs one BDD, and this entire thing constructs an existential BDD.
Yeah. So the AND here is an operation on BDD, correct?
Yeah.
And trans B1, B2 is itself constructing this BDD,
Yeah.
correct? Yeah.
Yeah. And
Because that you have defined it in terms of the basic operation on BDD is BXR, correct?
sorry. Yeah.
What is
yeah.
BXR?
This is basically this transition relation.
No, I understand, but explain what is BXR.
So BXOR is exclusive OR, which says that A and B can't be the same.
That is right.
So
No, but is that constructing a BDD or not?
That is constructing a BDD.
That is right. Okay. And do you understand, class? Do you understand that? So each of this is constructing a BDD, and then Zubin is doing a operation, okay, on those two BDDs, okay, and then so go slow and explain. I don't know. I mean, either. Guys in the class, you should interrupt and ask questions. Okay, just staying quiet, means that it's being you're understanding it. Okay, so
over here we're asking
Kapil
for.
is the only one who's asking question. Kapil, do you understand?
Yes, sir. This example I understood.
So you said, okay, so each of them is constructing a BDD. Do you understand that? Class, do you understand that? B exists is an operation on, it takes three arguments, two BDDs and a variable, okay?
No, it takes, one is the manager, which is just the state of
That's
CUDD.
fine, yeah.
That is, so that we can ignore.
Everything takes manager, okay?
Yeah.
So at that level, please explain.
So
okay?
the first argument is the formula you want to quantify over, and the second argument is the variable that you are existentially quantifying over.
Yeah, but in this case, that formula argument itself is the result of applying an AND operation on two BDDs. Am I right?
Yeah.
Correct. Okay, explain it at that level, okay? Since
So-
they are new to BDDs, okay? So class, do you understand how the BDDs are being constructed here? Please, in chorus, say yes or no.
Yes. Yeah.
Yes, sir.
Okay. So exists. So everything here is a formula. You're manipulating only formulas, okay? So each time you do, you get another formula, which represents something that you want to represent, okay? So what exactly, I'm asking a question. So he has, what does this formula starting with B exists represent? as a Kripke structure? Can someone in the class answer? I know it represents the existential formula, but it has some meaning in terms of image and so on. Can someone answer that?
So it just means that V1 and V3 are related via two transitions, right?
You are computing the two-step
Image under.
image. Okay, that is the kind of answer that I expect. Okay, so now Kapil and others who Rishikesh who asked, do you understand that? This is exactly what you did in your assignment 1, assuming that you have finished that. So when you did compute the thing, and I think it is Kapil or someone who asked, oh, someone even asked, oh, can I use the existential quantification? Okay. So when you do trans V1, V2 and trans V2, V3, you're applying the transition relation twice. Is that clear, class?
Yeah.
Kapil, is that clear? I want an answer from Kapil, okay? Is he still here?
Yes, sir. Yes, sir.
Okay, so that's what is happening here. So what does this whole thing can be viewed as a formula, okay? The only thing that's happening here is it's being represented as BDD. Once you get that, now you have a formula that represents the two-step image, two-step image, okay? What do you expect this to be? What are the satisfying assignments to this formula? Can someone answer?
So if V1 is any arbitrary initial state, then anything can be the.
It is arbitrary.
So in essentially V1 and V3 have to be the same thing. So
correct.
As in, yeah.
Exactly right, because it flips and flips again. Therefore, if V1 is a 0, V3 has to be a 0. If V1 is 1, V3 has to be 1. Okay? So those are the satisfying assignments. The only difference is that, so now you see, this is exactly a formula. So internally, it is being represented as BDD. So, and now Zubin is going to illustrate how you could extract satisfying assignments, okay?
So what we're doing here is we're calling the allsat function from CODD, which basically gives us all satisfying instances of this. And each instance can have, so if you look at this data type sat bit, it can be either 0, 1, or don't care, where it doesn't matter what a variable is, the formula will be true either ways. So this cuts down on the number of satisfying instances you have to print out by, in the best case, an exponential factor, because otherwise you'll have to give an instance with 0 and an instance for 1. So in this case, we have two satisfying instances, 0 where we start with 0 and end with 0, or we start with 1 and end with 1.
So what have you used don't care for?
So don't care is
that is
for
existentially quantified out.
Yeah, that is existentially quantified out, that is V2.
Yeah.
So
So we
it
can
doesn't,
infer that the states will be Boolean, means each component of the state will be Boolean, right? Not anything.
Exactly correct.
Okay.
That is how it has always been. Okay. So I mean, because in SAT, you were using SMT, you had the luxury of making it numbers. In BDDs, you don't. Okay. BDDs are just Boolean. So that was an aside. Okay. In SAT, you happen to have, actually, strictly speaking, in Boolean SAT, you do not have. Everything has to be on Boolean. And since we are dealing with only finite state systems, we always encode our state as in terms of Boolean, okay? And especially so now because BDDs are only representing Boolean functions. So for that reason, state consists of state variables. Each variable takes a bit, and entirely the whole thing will be a function of a bunch of variables, okay? And transition relation happens to relate the pre and the post state variables, each of which is Boolean, and therefore it'll be a relation between a pre-state which has two. In this case, it's only one variable, so it is in addition of those two variables. Yes, the state variables.
Sir, and how big will be the Kripke structure in your test cases?
Well, you tell me. I mean, in our examples you're saying, or in general you're asking the question?
Means in the test cases which we will use to
Well, that you could, no. But when you build it, for that is a good question. Oh, no. See, all these algorithms that I've shown so far, they take S as a symbolic state. They are kind of, it doesn't matter how many variables there are, okay? But in practice, when you implement, of course, you have to you have to specify the total number of variables, okay? So when you build the transition relation and the initial state, the Kripke structure itself will have to define what the number of state variables are. Or what you can do is we could say, well, that's a good question, Kapil, because that is a good question in that it is important for you to implement, which I had not specified as part of the problem. I think, Zubin, you can make a recommendation also, or the class itself can make. So what you do is you have a bound on the number of variables that your program, your Kripke structure, the Kripke structure that you're able to handle, okay? So we can impose, some, these things.
You can take it as an input also, right? You can, your first input can be the number of.
So you could define that as part of the Kripke structure, the input, and then you can say that the state variables have those many number of bits, okay? And that determines the total number of variables that you will ever have to create, okay, to represent that structure. And you could throw in a few extra variables, okay, because you may need some variables, in between. So that is something, you're right, that you will have to give as an input to BDD. So it's a good point that was raised. Yes. Does that answer, Kapil?
Yes.
Yeah. For the rest of you, I think the variables is an input that you have to, even in SAT, for example, although you don't need to give in advance, you can create on the fly. Whereas here, I'm not sure. I don't know if the manager package here allows you to add more variables later on. Zubin?
Yeah, you can.
Yeah, that is one
variables whenever you
that is one thing is a little bit, you can't say it is a restriction, but rather you can understand why it is so, because the variable ordering, etc., is very much a part of BDD. So you have to do the thing. Another question that that comes up that I'm surprised that people haven't asked is, where is the variable ordering that you're using defined, Zubin?
So that's just defined by the index.
Okay, that's the thing that maybe you did mention it. Yeah. So whatever the number that you give is the variable ordering. Okay, and since that variable ordering has to be defined in advance, so therefore you will have to give to the manager the number of variables. And actually, don't you need to specify the number of nodes also, the size?
No, I don't think so. No, you don't.
Okay.
Yeah. You have to whenever you create a new node, you have to tell the manager that you've created a node, and then yeah. So every time you create a node, you have to tell the manager in C that you
No, no,
have created this node.
complete. Yeah. Okay. Go ahead. What do we show? What are we going to show?
I'll- yeah. So, yeah. So okay, I don't have the code here, but uh, let's see. Yeah, so every time you create a variable, you have to tell the manager that, okay, I've created this variable and this variable is still alive. And when you stop using that variable, you have to tell the manager, okay, I'm not using this variable anymore. And I'll upload some links to tutorials which have all that information.
Yeah, that part is still not clear. Okay. So why is that important? I thought that you never need to destroy. You have to tell them. Why do you need to tell them to destroy? Why do you ever need to destroy a variable?
When you want to reuse the a variable in your formula for performance reasons or something, or you want to reuse
That
your
aside,
formula.
okay, so those, okay, let's not confuse the thing. So maybe those features are there, but in any case, the point is that you will have to tell it the number of variables that you will have to create in advance. Okay. Now run complete the thing. So where did it print out the satisfying assignment? Yeah.
It printed out the assignments here. So the two satisfying assignments are 0, don't care 0, and 1, don't care 1.
Okay.
I think that's it.
So,
Yeah.
as
So
an
I'll stop sharing.
A class exercise, okay? Now, this is anyway, you will need to you need to implement as part of your CTL model checker. So by next class, I want everyone in the class, okay, to have implemented AX and EX, okay? I've already discussed in class and in several times in the class and even in that, okay, maybe I will actually show you this thing, okay? So I had, okay. Oh, I'm not, okay. Can I take over? I mean, as I, you know, okay. So before I move on and describe what I want you to do, you know, I will specifically show, I want you to implement AX and EX, okay? The BDDs, a program that will, I mean, I will explain it. I want you to implement AX and EX, okay? I will show you exactly what I want you to do so that everyone would have done that using BDDs you would be familiar with. And if you're not able to do it, you will make a list of the questions and come ready for you know, the questions for the class, okay? Before I do that, do you have any questions on the BDD construction part of it, okay? Or do you want to see, is there any other example that you can construct? You know, on this is, or you want to construct a, okay. Yeah, any other questions? You see, there's a, yeah, I would love to hear a yes, even if it is, or a no. Okay, that's, you know, don't keep me guessing, please. I mean, I'd, you know, love to hear.
I have some questions. Okay, I have just some, but it's not directly related to the BDD part.
Okay. Yeah. So that's before, but before I switch, because the BDD part we can come back. Okay. But do you have any questions on the BDD part? Okay. I mean, I'm sure. I mean, this is not the end of the the thing. I mean, you're encouraged to have and ask questions later on also. So it's only because if you want me to show my part. Okay, ask the question, Diganta.
No, so since we were just discussing the number of variables, I just wanted to know, like when we are going to test out our thing, what is like a reasonable number of variables that we can try it out with? Because like with new assembly and all, we tried, I think we never tried more than 10 variables. So from a performance standpoint, what is a reasonable number of variables to try this out?
Well, look, you know, yeah, so that's a question. See, you are implementing a prototype, okay? So I'm not going to make the efficiency as part of it. The whole point of this exercise is, I hope that you will have, I sincerely am hoping that this will be a learning experience, because see, we can talk at this level of theory and so on. So there we have, unless you do something hands-on, you will not get a real good idea of what exactly this fixed point computation is. It may seem very esoteric, okay? But it's only when you do the thing, okay? So I'm not going to expect super duper performance from you, and that is not going to be the criteria. I look at whether you have implemented it, and I think even with very simple, non-engineered implementation of the kind that where you do not devote any time engineering for performance, you should be able to get, just by, the BDDs up to, I would say 10, 15 bits, okay? Variables, Boolean variables, easily, okay? It's only when you're getting it to 32 and 64, and then you have these transition relations and it also depends on the transition relation, what kind of operations they're doing. If they are all doing very Boolean, connective, all of them eventually are Boolean connective. So in terms of, if it is implementing arithmetic, for example, if you're doing adds, shifting, etc., is no big deal. Addition is no big deal. If you start doing multiplicative operations, then if you get beyond 32 bits, you will start getting issues, okay? This is purely at the Boolean structural level. Now, when you're doing model checking, you are iterating over image computation, okay? The existential quantification can blow up the, generally it can blow up the size, okay? But as long as the intermediate functions, what are the intermediate functions that you get during model checking? These are all some states reachable, okay, in some ways, okay? And that's what you're doing in CTL model checking. So you start with some states that are satisfying all of P, then something that are reachable 2P in one step, two step, and so on. That's what model checking is primarily doing. So if those intermediate reachable states, those functions that are representing them are compact, then you don't get it. So in general, what I'm saying is that you should be able to get, even with naive implementations, up to 15 bits, variables. 32 in well-engineered one, you should be able to get to 32, as long as the depth of these reachability depth are not too big, and the intermediate functions that you generate, Boolean functions that you generate to represent the intermediate states, are still don't have a blow up. So you'll be surprised, up to 32 bits without too much arithmetic operations, you should be able to get, okay? Does that answer your question? Because it is impossible, Diganta, to give a precise answer, okay?
Yeah, this is, okay, so I'll just try like 10, 12 bits, I guess.
Yeah. Now, you could immediately, you can get, the thing would be, what are the number of components that you have in a thing. When you're composing asynchronously or synchronously, then you can have state explosion and so on. No, I mean, for simple things, you should not worry about increasing the bit sizes. Yeah. Okay. So it's only when you go to beyond 32 bits that I suspect that you can have some problems, or when you have very deep fixed point depths, okay, that then you may have issues. If you're, again, that once again depends on your transition relation, okay? So any other questions? Okay, so I'm going to have you, take the sharing away from you. Oh, you're still a co-host, that's okay. So you stopped sharing, so that's fine. So let me. Oh, how do I share? What happened to the? Okay, so are you all there? So what I want you to do is exactly this: implement AX, EX, and AX, okay, as BDDs. That is, you start with he'll upload. You already uploaded that code, correct, Zubin?
Sorry, which one?
No, have you uploaded? I mean, I'm asking you to upload. Have you uploaded anything related to BDD or
No, not yet.
your code?
Not yet, no.
Okay, now that you should have already done. In any case, you upload whatever code that you showed last time, as well as the code that you did today, okay?
Yeah.
What I want you to do, class, is implement EX and AX, this operation, okay? Which will, you don't need to, you don't need to implement all the, the parser, everything, okay? That is for the, for the project, okay? You could have EX and AX defined, this part in a generic way, given two functions, and then you could hardwire, okay, to test it what your functions are. I mean, your transition relation and the P, the T and P can be, then you could individually define, just like Zubin defined, okay?
That should be P of S prime, right?
What?
For the first formula, that should be P of S prime, not S.
Are you saying that what I have there is wrong? No, that's okay. I can make mistakes. No, but I think this is S prime is correct here.
It should be S prime, right? It's written S. P of S, it's written. It should be S prime.
You're right. Okay, that's good. That's a good point. Yes, it has to be PS prime. You're right, man. Yeah. Okay, so there's a mistake there. This has to be PS prime. I think what is being quantified over is correct, but it is PS prime. Now, what you can do is you can do the same problem. I mean, once you define this as in terms of BDD, all I want you to do is to implement this, and then for any given T, you can fix the number of variables. You can actually target. Try and do it for the fixed point problem. You just pick whatever transition relation that you have. Let it have your state have, say, 2 or 3 variables. Okay, construct the BDD function, define a function which constructs the BDD representation for the formula for EX and AX as I have defined here. Okay, and then you evaluate it out, okay, and to see you know what you know what you get, okay. Then you can try for repeated AX and EX, okay. So you will get a hang of it, okay. And that's what I want you to do. At least I want you to do, each and every one of you, okay, to please do it so that it'll help you thrash out any doubts that you may have for BDD. And after that, you can get all satisfying assignments here. I mean, you had to do a lot of work in for a SAT solver in order to get, because you had to do one at a time, okay. Whereas here, computing all satisfying assignments once you construct the BDD is very easy. All you have to do is chase all the paths in the BDD to do it, which you don't need to do. They're all available as library of functions. Zubin, have you uploaded the list of functions that you were displaying, the document that contains the list of functions to Moodle? So
that's
huh?
the documentation of CODD.
Yeah, maybe you should mention
Yeah,
it.
I'll put a link to all of those.
Okay. So yeah, I mean, for this exercise, I don't think you need anything beyond what was described. Maybe you need not, and so on. So you can actually do AX both this way. There is for all also implemented. There is a function implementing for all. Zubin?
Yeah, there is.
Yeah. So you can try both these approaches. You can do it using existential with a negation and this one. And what I'm saying is then test it out. Take your transitions Kripke structure to have at least two variables or three variables, and then try this out. Okay. And we will continue this thing. And I will take you what I intended to do, which I did not get today. That's okay, because Kapil's questions, basic questions, really helped to hopefully, I'm thinking, to sort out some of the basic things about BDD. I do understand switching from a SAT paradigm outlook to a BDD outlook can be a little bit, sometimes is giving you, may startle you, but believe me that implementing this will not be very, very difficult. But I will keep in mind, so that since it's an individual project, as to the scoping of the project. So I don't take offense at all in anyone who makes even bold suggestions. So don't take me wrong, on that. So I encourage those kinds of feedback, questions, as well as comments. Okay. Good. So I still want to keep the scope at that level. So, and let's see. I mean, as we, I will, think about, couples' suggestion, whether this is a bit too much or not. Okay, and decide on.
Sir, could you also provide a parser for Python? Like, I'm not very clear how we should.
Yeah, that's the question. So the class now, I mean, everyone is here except one, I think. Okay, between Python and, okay, there's one, Diganta, who wanted to use C or C++. The rest of you are satisfied with, I know that Zubin guaranteed existence of a interface for Haskell, but have you, because there are some people who want to program in Python, are you sure, Zubin, that there is well supported?
Yeah, there is a BDD package for Python, which can use CODD as a backend.
There is a what? Can you repeat?
There is a BDD package for Python, which can use CODD as a backend.
Yes, sir. I know about the existence of the package, but syntax in which it takes the input as the formula as input is a bit different from what we did in Haskell. So we might need a parser for that, I thought.
So now you're,
So
so he's saying that the interface.
We'll define a really simple input format that only uses like single characters and numbers for.
Okay, let's let's think about that, Zubin. Huh?
Yeah.
For this exercise that I have asked you to do before next class, that is not an issue. Okay, so you could hardwire that formula in terms of the operations right into the code. Okay, Kapil, do you understand that? And the class, do you understand that? What I want by next class?
Yeah.
Yeah. Yeah. So, but that question that Kapil, I will take it under advice. Okay. So he's asking to see if we could provide a way to just parse from string to. I mean, provide the parser. I mean, the parser means in this case it has to construct the BDD itself. Okay, for T and I and then P. Okay, if we provide that. What do you think, Zubin? Do you think that you're asking for that, Kapil, because you think that it is hard to do in the Python interface, or you want to just simplify things for you?
Yeah, I want to simplify things for me.
Okay. Okay, I will think about it. Okay. So, and Zubin, I don't want to commit without discussing with Zubin. Yeah. Okay. Any other questions? I know I didn't get into any of the top level structures, details, etc., which I will in the next class. Yeah. So that should help you in deciding what is involved in each of those things. Yeah. Okay. So if there is no further questions, I'm going to stop sharing. Stop recording.